A machine learning model was given every sonar contact ever logged at Loch Ness, 66 years of readings, thousands of individual data points, numbers that had been sitting in filing cabinets and old expedition reports since the 1950s. And when the model finished sorting through all of it, it did not find a monster. It found something stranger. It found a pattern. The same depth range, the same narrow stretch of water, the same rough time of year, showing up again and again across data collected by completely different teams using completely different equipment across 7 decades, who never once compared notes with each other. Stay with me for the next few minutes because I am going to walk you through exactly what that pattern is, how researchers found it, and why a growing number of scientists now think it deserves a serious second look. And if you want more real investigations like this one, hit subscribe. Now, because this channel only covers documented history and genuine evidence, never invented stories dressed up as fact. To understand why this pattern matters, you first have to understand just how much raw data actually exists about Loch Ness. This is not a case of one blurry photo and a handful of campfire stories. Since the 1950s, dozens of separate scientific expeditions have swept the loch with sonar, and nearly every one of them kept detailed logs, depth readings, contact duration, signal strength, water temperature, time of day, even boat position. For most of that history, those logs sat in isolation. A 1962 expedition's numbers never got compared against a 1987 expedition's numbers, a university. Research team in the 1970s had no easy way to cross-reference its findings with a BBC-funded survey conducted decades later. The data existed, but it existed in silos, scattered across paper archives, microfiche, old hard drives, and out-of-print academic journals. Nobody had ever actually sat down and merged all of it into a single, searchable dataset. That changed only recently, when a small team of researchers began the tedious work of digitizing decades of archived sonar logs and feeding the combined dataset into pattern recognition software originally designed for entirely different purposes, tools built for spotting recurring signals in noisy environmental data, the same basic approach used to detect seismic patterns before earthquakes or migratory patterns in ocean wildlife tracking. The idea itself is not really about hunting for a monster. It is about doing something remarkably simple that nobody had the tools or the patience to do before, taking 66 years of scattered, inconsistent, individually inconclusive sonar readings and asking a machine to look for anything that repeats. Human researchers are very good at spotting a single dramatic anomaly. They are much worse at noticing a subtle statistical pattern buried across thousands of readings collected by different people using different equipment in different decades. That is exactly the kind of task modern pattern recognition software excels at. Feed it enough numbers, and it will flag correlations that would be effectively invisible to anyone manually paging through decades of expedition reports. So what did it actually find? 3 things stood out, and each one deserves its own explanation because none of them prove anything supernatural. But together, they form a pattern that is genuinely difficult to dismiss as pure coincidence. The first pattern involves depth. Across data pulled from Operation Deepscan in 1987, the BBC's 2003 sonar survey, and several smaller expeditions in between, unexplained contacts clustered, overwhelmingly in a specific depth band roughly between 300 and 600 feet. That might not sound surprising at first, since Loch Ness itself only reaches about 750 feet at its deepest point, so you might assume contacts would naturally spread out across the available depth range. But they did not. The vast majority of ordinary sonar activity, boat traffic, fish shoals, floating debris, tends to concentrate much closer to the surface, generally within the top 100 feet, where light, temperature, and food are all more abundant. Now, the unexplained contacts set noticeably deeper and more consistently, within that 300 to 600 foot band than ordinary biological or mechanical activity would predict. When the model compared this distribution against a simulated random spread, the clustering showed up as a statistically meaningful pattern rather than noise, the kind of thing that would make a data scientist stop and ask a follow-up question rather than move on. The second pattern involves geography. Loch Ness is roughly 23 miles long, and you would expect unexplained sonar contacts, if they were random noise or equipment error, to be spread fairly evenly along its length. They were not. When the model plotted every unexplained contact from every available expedition onto a single map of the loch, a disproportionate number clustered around a relatively narrow stretch near Urquhart Bay and the deeper trench sections further south, areas that also happen to have the loch's steepest underwater walls and its most complex underwater terrain. Now, there is a very reasonable, very mundane explanation for at least part of this. Those are also the areas researchers have historically focused the most equipment and attention on, simply because the terrain is more interesting to study and the water is deepest there. More scanning naturally produces more contacts, explained or otherwise. That selection bias is real, and any honest treatment of this pattern has to acknowledge it up front. But even after researchers attempted to statistically adjust for how much scanning effort each area actually received, correcting for the fact that some parts of the loch were simply searched more often, the clustering around that same stretch of water did not fully disappear. It weakened, but it held. The third pattern, and arguably the most interesting one, involves timing. When the model cross-referenced the date of every unexplained contact against water temperature records for the loch, a seasonal pattern emerged. A noticeably higher proportion of unexplained contacts occurred during the warmer months, roughly between June and September, compared to the colder months of the year. Again, there is an obvious mundane explanation sitting right there. Most expeditions were scheduled during the summer anyway, since that is when weather conditions make field work practical and when tourist season brings in the funding and volunteers that make large expeditions possible in the first place. More summer searching should naturally produce more summer contacts, regardless of what is actually down there. But when the researchers controlled for expedition frequency by season, meaning they adjusted the numbers to account for the fact that far more searching happened in summer than winter, the seasonal skew in unexplained contacts was larger than the seasonal skew in expedition activity alone would predict. In plain terms, contacts were showing up more often in summer than you would expect purely from more people looking during summer. It is worth pausing here to be completely clear about what this kind of analysis can and cannot tell you, because this is exactly the point where a lot of coverage of stories like this tends to go off the rails, into wild speculation. Pattern recognition software does not identify creatures. It does not distinguish between a biological explanation and a purely environmental one. All it does is take a large pile of numbers and tell you, with a measurable degree of statistical confidence, whether a pattern exists or whether what you are looking at is more likely to be random noise. What this particular analysis found is a real, measurable, non-random pattern in where, how deep, and when unexplained sonar contacts have occurred across 66 years of data. What it did not find, and importantly did not claim to find, is any confirmation of what is actually causing that pattern. That distinction matters enormously. So let's walk through the range of explanations that remain genuinely on the table, because a defensible scientific pattern like this one deserves a full accounting of the possibilities, rather than a jump straight to the most dramatic option. The most straightforward explanation involves the loch's underwater geography itself. Remember that Loch Ness sits inside a trench carved along the Great Glen Fault, later scoured out further by glaciers, which means its underwater terrain includes steep walls, sudden drop-offs, and complex basin shapes rather than the gentle, predictable slopes found in most lakes. Sonar pulses bounce differently off complex terrain than off flat, uniform bottom. It is entirely possible that the depth and location clustering researchers found simply reflects where the loch's geometry is most likely to produce confusing secondary echoes, meaning the pattern is really a pattern in sonar error rather than a pattern in anything actually swimming through the water. This explanation does not require anything unusual living in the loch at all, only that certain sections of underwater terrain are more prone to generating false or ambiguous readings than others, and that those sections happen to be the ones getting scanned the most. A second explanation involves the thermocline, the layer where warmer surface water meets the loch's much colder deep water. This layer is not fixed. It shifts seasonally, typically sitting closer to the surface in colder months and dropping deeper, becoming more pronounced. During the warmer months, when the temperature difference between surface and depth water is at its most extreme, a stronger, more clearly defined thermocline bends and scatters sound waves more dramatically, which could plausibly explain both the depth clustering, since sonar distortion would concentrate right around wherever the thermocline happens to sit that season, and the seasonal clustering, since a more pronounced summer thermocline would generate more confusing readings than a weaker winter one. This is genuinely one of the more compelling, mundane explanations, because it accounts for two of the three patterns, simultaneously using nothing more exotic than basic water physics. A third explanation, and the one that keeps this story from being fully closed, involves biology, specifically the fact that this depth and seasonal pattern lines up reasonably well with what is already known about eel behavior in the loch. Remember that a 2019 environmental DNA study led by researchers at the University of Otago found an unusually large quantity of eel genetic material throughout Loch Ness, more than any other species detected. Eels are known to alter their depth and activity patterns seasonally, often moving to different depths as water temperature changes and as they respond to shifts in food availability and their own reproductive cycles. If the loch does host an unusually large population of eels, and if some individuals within that population genuinely do grow larger than typical for the species given the loch's consistently cold, food-rich conditions, then a seasonal shift in depth and activity among that population could theoretically produce exactly the kind of pattern the model identified. The problem, as researchers were quick to point out at the time of the original eDNA study, is that eels have a long, extremely flexible body shape that does not naturally produce the kind of solid, consistent sonar signature recorded during expeditions like Operation Deepscan in 1987, where multiple boats picked up independent contacts on separate equipment simultaneously. So while eel behavior can plausibly explain a seasonal and depth pattern in general, it does not cleanly explain the specific character of the strongest individual contacts on record. And that leaves the fourth possibility sitting quietly at the edge of the analysis. The one researchers are always the most careful about how they phrase that whatever is producing at least some portion of these contacts has simply not been identified yet. Not a plesiosaur, not anything requiring an explanation outside of known biology, but potentially some combination of an unusually large, unusually elusive resident species behaving in ways that current data collection has not yet fully mapped. This is the least exciting explanation in terms of headlines, but it is also the most scientifically honest one, and it is worth sitting with for a moment rather than rushing past it towards something more dramatic. What makes this AI-assisted reanalysis genuinely valuable, regardless of which explanation eventually turns out to be correct, is that it represents the first time anyone has actually been able to treat 66 years of scattered expedition data as a single connected dataset rather than a pile of separate, unrelated reports. Every previous investigation, going all the way back to the 1954 sonar contact recorded by the fishing boat Rival III, operated essentially in isolation. Each team analyzed its own readings against its own baseline, drew its own conclusions, and then moved on, leaving the next generation of researchers to start again from scratch. Nobody had systematically compared 1960s Loch Ness Investigation Bureau data against 1987 Deepscan data against 2003 BBC data against the 2023 Quest Expeditions hydrophone recordings, because doing that kind of cross-referencing by hand across incompatible old formats and inconsistent recording standards would have taken years of tedious manual work for uncertain payoff. Machine pattern recognition changes that equation completely. It can process decades of inconsistent, messy, differently formatted historical data, in a fraction of the time, flagging correlations that would be nearly impossible for a human researcher to notice by eye, simply because no single person could realistically hold 66 years of individual data points in their head at once while looking for a subtle statistical trend. Before going any further, it is worth addressing the obvious skepticism this kind of claim should invite, because a healthy dose of doubt is exactly what has kept this mystery honest for 70 years. Statistical pattern recognition is powerful, but it is also notoriously easy to misuse. And the history of data science is full of cautionary tales about researchers finding patterns that later turned out to be nothing more than an artifact of how the data was collected in the first place. Anyone treating this kind of analysis uncritically should be raising exactly the same objections a careful reviewer would raise. How large was the actual sample size of unexplained contacts? Across 66 years, since if the total number is only in the dozens, even a real pattern could still be somewhat fragile. How consistent were the criteria different expeditions used to label a contact unexplained in the first place? Since equipment and standards changed enormously between the 1950s and the 2020s, and a contact one team dismissed as debris might have been logged as unexplained by a differently calibrated team decades later. And how much of the clustering genuinely survives after adjusting for where and when researchers simply happen to be looking, since uneven search effort is one of the most common ways and entirely mundane. Explanation gets mistaken for something mysterious. These are not reasons to dismiss the pattern outright, but they are exactly the kind of questions any serious researcher would want answered before drawing firm conclusions. And the honest answer is that the sample size here, while larger than any single expedition ever had on its own, is still modest enough that some caution is warranted. It also helps to understand why nobody attempted this kind of unified analysis sooner, since the obstacles were not really about willingness, but about practicality. Digitizing decades of paper logs, some handwritten, some using now obsolete measurement conventions, some stored on formats that modern software cannot even read directly, is genuinely tedious, unglamorous work that offers no guarantee of finding anything useful at the end of it. Most individual researchers focused on their own expedition and their own funding cycle simply never had the time, resources, or institutional support to go back and manually reconcile their own findings against 40 or 50 years of somebody else's archived data. It took the current moment, when pattern recognition tools have become accessible enough for smaller research teams to apply them to messy historical datasets, and when enough decades had finally accumulated to make the underlying dataset large enough to be worth the effort for this kind of retrospective study to become realistic at all. In that sense, this analysis is less a sudden breakthrough than the natural next step in a very long, very patient scientific process, one that simply had to wait for the right tools and the right amount of accumulated data to exist at the same time. It is also worth appreciating just how much this kind of retrospective analysis depends on the original researchers having done careful, disciplined work in the first place. None of this pattern would exist to find if the teams behind Operation Deepscan, the BBC's 2003 survey, or the 2023 Quest expedition had not meticulously logged exact depths, exact locations, exact timestamps, and exact contact durations, rather than simply noting that something unusual happened somewhere in the loch. Decades of unglamorous, methodical record-keeping by researchers who mostly never got a definitive answer for their own individual efforts turned out to be exactly the raw material a modern algorithm needed to notice something none of them could have seen on their own. That is a genuinely underappreciated part of this story. 66 years of researchers doing careful, disciplined work that produced no dramatic answer in their own lifetime. Work that only became meaningful once enough of it existed to feed into a tool nobody had access to when most of that data was originally collected. So where does this leave the actual mystery? Not solved, and it is important to be upfront about that, rather than oversell what a statistical pattern can prove. Nobody has produced a photograph, a physical specimen, or direct genetic evidence of any large unidentified creature living in Loch Ness, and this analysis does not change that. What has changed is more modest, but still genuinely significant. For the first time, there is a measurable, cross-referenced, statistically meaningful pattern connecting 66 years of independently collected sonar data, a pattern that survives basic attempts to explain it away through selection bias and expedition scheduling, even if it does not survive as proof of anything specific. The honest scientific position is the same one researchers have held since Operation Deepscan first produced its own unexplained readings back in 1987. There is something in this data that current explanations do not fully account for, and admitting that gap, honestly, is not the same thing as claiming to have solved it. If you had to guess, based purely on everything actually covered here, does the depth and seasonal clustering point toward thermocline distortion? An unusually large eel population behaving in ways not yet fully mapped or something researchers genuinely have not identified? Drop your honest read in the comments, because after 66 years of real documented data collection, an informed guess grounded in the actual pattern is worth far more than another exaggerated headline. If you want more stories built entirely on documented history and genuine data rather than invented claims, dressed up as breaking news, subscribe to this channel and turn on notifications, because there's a lot more of this kind of careful investigation still worth digging into. Thanks for watching, and I will see you in the next one.